Hello everyone, this is Kami and welcome to my seminar. I will be presenting recently paper titled Measuring the Photoelectron Emission Delay in the Molecular Frame. In early quantum theory, it was natural to ask whether time could be treated as an operator, just like position or momentum. In 1926, Pauli explored this idea, but found that time is not the self-adjoint operator. It acts as a parameter that runs continuously and cannot be measured directly. However, when restricted to scattering state, one can define a self-adjoint operator corresponding to the Wigner time delay. The extra time a particle spends in a scattering region comparing to free flight, which is relative to the scattering phase shift. In this graph, the blue curve is a free plane wave. It propagates without potential. The orange curve shows the same wave after passing through an atomic potential. As a result, the phase of the plane wave is shifted by a scattering phase delta. In the case of potential scattering with spherical symmetry, Wigner time delay for a single partial wave is defined as twice the energy derivative of the scattering phase shift. In this process, the electron comes in, interacts, and then leaves, leading to a total phase shift of 2 delta. But in photoionization, electrons are only emitted from potential region, so it is considered a half scattering process. The Wigner time delay in photoionization is given by the energy derivative of the phase shift. Since such emission time is in the attosecond region, only attosecond XUV pulse provide both sufficient photo energy for ionization, ultra-short time resolution to resolve delay. In other words, allow us to see this ultra-fast dynamics in real time. This is photoionization from two initial states, which is induced by XUV radiation. To define a time delay, we need a reference. That's why we use two initial states. The photoelectron waves pick up different phase shift, delta A and B. With the help of inferent prompt pulse, this time delay can be measured indirectly. This is the basic principle behind the two main techniques of photoemission time delay, attosecond streaking and rapid. Attosecond streaking and rapid are both photoionization techniques with different time delay measurement method. In streaking, the red line is field cycle IR pulse. The blue one is isolated attosecond XUV pulse. The XUV pulse ionizes the atom, releasing an electron with a specific kinetic energy. Because of IR field, the electron is accelerated or decelerated. By changing the delay tau between the XUV and IR pulses, we ionize the electron at different times and measure their final energies, producing a stimulated streaking spectrogram. By comparing the measured result with the case where electrons would be emitted instantly, we observe an energy shift, which can be converted into a time delay. In method of rapid, red line is a many-cycle IR pulse with frequency of omega. The blue one is XUV pulse string, consists of many odd harmonic frequency, and higher harmonics can ionize the atoms. As a result, in this photoelectron energy spectrum, the energy peaks are equally spaced by 2 h bar omega, which are called main band. The IR field allows two photo transitions. After observing one harmonic, the electron can either observe or emit one additional IR photon, which are called sideband, a new peaks between the main bands. This sideband only appears due to interference between two quantum paths. Here is the delay spectrogram. You can see the interference pattern or oscillation, the main band, sideband, main band. By fitting this oscillation, we can extract phase from it, which gives us the time delay information. Ultimately, however, both rapid and streaking do not measure the pure Wigner time delay. It is a total delay that includes effect from the IR field. Both of them require attosecond time resolution, which demands extremely stable pulses and a controlled environment. Is it possible to measure time delay in photon ionization without attosecond pulse and IR field? Or can we measure it even without measuring time? This is the first motivation of the paper. A photoelectron emerging from an atomic potential gains a half scattering phase shift, which is isotropic in atoms. However, in more complex systems such as molecules, the potential is anisotropic. The phase shift depends on the emission angle with respect to the molecular axis. So the second motivation is, can we measure the time delay as a function of the emission angle in molecular frame? To answer it, we need a more general definition of Wigner time delay. Taking the phase of the dipole matrix element between the initial state and the final state, and then taking its derivative with respect to the energy. The dipole matrix elements contain the full information about the photoionization process, including its angular dependence. And the square of it gives the molecular frame photoelectron angular distribution, that is the MFPADs, what we will measure directly in this paper to extract the time delay information. Now let's look at the theoretical derivation of MFPADs. In a photoionization reaction, a molecule observes a photon, then emits an electron, leaving behind a molecular ion. When this emitting electron is in an arbitrary molecular potential, its wave function can be expanded into a series of spherical waves. This is photoionization matrix element. Between a bound state and a scattering state, the dipole operator is expressed in the laboratory frame, while both wave functions are in the molecular frame. We have to transfer it from the laboratory frame into the molecular frame using Wigner rotational matrix. Substitute equation 2 and 4 into 3, we can get the full expression of the photoionization matrix element. Simplify it. The total photoionization transition amplitude T becomes a coherent sum of partial transition amplitude A. And these elements need to be numerically computed in a complex molecule. In conclusion, MFPAD is a coherent superposition of spherical function with numerical weight. And the square of the total transition amplitude gives the photoelectron detection probability or angular distribution, which depends on the molecular orientation and emission angle. And in this paper, we study co-ionization of CO molecule, we only consider two geometries. One is where the molecular axis is parallel to the polarization direction, and the other is where it is perpendicular. That is why the only relative Euler angle is beta. And the photoelectron emission in the molecular frame is described by the spherical angle theta and phi. Here is the total amplitude. We measure the photoelectron angular distribution is as a function of angle and kinetic energy. After obtaining the complex transition amplitude, we extract its phase and takes its energy derivative. That is energy and angle dependent Wigner time delay for photoionization. Now we come to the experimental setup. To measure MFPADs, we use COLTRIMS, which is a cold target recoil ion momentum spectroscopy. A supersonic CO gas jet is intersected with the synchrotron photobeam. Ion pairs are generated in coincidence after K-shell ionization and subsequent order decay. Guided by the electron and magnetic field, the resulting oxygen and carbon ions fly to the recoil ion detector, while the electrons fly to the electron detector. The fields are always optimized, depends on the energy range you want to measure. By detecting where and when each particle hits the detector in coincidence, the initial momentum can be deduced. P1, P2 are momentums of ions, PE is electrons. In diatomic case, the ion fragment along the initial molecular axis. The angle between the delta P and the PE is electron emission angle. This is a schematic diagram, shows multiple measurement results of the momentum vectors. Inside the CO gas jet, molecules are randomly orientated. For polarized average MFPAD, we don't care how molecule with respect to polarization. We just count how many electrons are at each angle. The distance from the origin to each point represents the number of detected electrons in that direction. By connecting these points, we obtain the PAMF part. But in our case, we care how molecule is orientated. We want two figuration, beta is 0 and beta is pi over 2. For example, if the polarization is given in this way, we want beta is pi over 2. We only choose this molecule and sort them by angle to plot MFPAD. Now we finally come to the results of the study. This is the same total amplitude as previously shown. Here is an example of emission pattern for co-electron emitted from a CO molecule. The electron energy is 18.8 eV. Black dots are the measurements. The molecule is oriented along the light polarization vector. That means the beta is 0. Only sigma partial wave with M is 0 contributes to this channel. This is the corresponding sigma channel MFPAD. And the red line is a fit to the bad dot, black points, employing partial wave up to L is 4. And the fit can give you all the A or even everything inside this square. A similar procedure can be followed for molecular oriented perpendicular to the light polarization when beta is pi over 2. In this case, only pi partial waves with p is plus minus 1 emitted contribute to pi channel. Its MFPAD is given by this. Now let's back to the sigma channel MFPAD. After fitting it, we extract the complex wave function. And the phase of the wave function is calculated and shown in figure B. The oxygen atom is located at theta is pi. The carbon atom is at beta theta is 0. You do the same measurement for a slightly higher energy, for example 18.9. By performing the same extraction, then plot the phase again, it might look like this. It's just an example. And after subtract two phases, blue from red, derivated by the energy difference, the corresponding molecular frame Wigner time delay are obtained. Here is the Wigner delay virus with the emission angle. However, it should be stressed that experimental Wigner delays are only defined up to a relative scale, because the global phase of the wave function is not accessible. Thus, the energy and angle-dependent delay offset is missing and cannot be determined from the experiment. Nevertheless, this problem can be fixed by calibration to the theory. This row shows results from theoretical modeling of photoemission process. Red line is relaxed core, blue line is frozen core approximation. Experimental data lies in between these two. And figure E, F are corresponding phase and the Wigner delay. Importantly, theory provides delays on an absolute scale. Because there's no unknown phase, everything is fixed. Therefore, we can shift the experimental data to match the average theoretical delay at each energy. Finally, we can then plot the complete experimental Wigner delay map. This row are experimental results for an electron energy of 8 eV. You can see in the Wigner delay map, it exhibits distinct features. It shows a sharp maximum and a deep minimum. Unlike the previous angle result measurement at fixed photo energy, an additional experiment scanned photo energy up to 20 eV. Figure AC are result of Wigner delay as a function of emission angle and in two orientation. The Wigner delay is represented by the color scale. Figure BD are from theoretical modeling. For sigma orientation, this yellow and red region indicate longer Wigner delay. The reason is the presence of the sigma-shaped resonance, which is a broad resonance feature that appears only for sigma's orientation with a maximum at around 10 eV. And shape resonance forms when the centrifugal potential builds a potential barrier that traps higher angular momentum emitted electron waves. I'm going to explain this. Here is a schematic graph of each potential term and its composite in CO molecule. The efficient potential is the sum of centrifugal potential and molecular potential. Centrifugal potential is decided by angular momentum L. This potential barrier occurs due to the centrifugal potential. When a wave passes through it, it can get trapped. For lower angular momentum, like 0, 1, 2, there is essentially no barrier. But when the angular momentum is higher, such as 3, the potential barrier forms. If the energy is above the barrier, the electron escapes. That's a scattering state. If energy lies just below the top of the barrier, it will be temporarily trapped then escape. That is quasi-state, or we can call it shape resonance. If the energy is too low, the electron stays bound. And that's why this yellow and red region has longer time delay. That's how the shape resonance forms. Finally, we come to the conclusions of this seminar. Thank you for your watching.